I want to just go over quickly this learning resource from Unit 5 on image generation. Some of the stuff is relatively new, so I'm recording a new video in here in 2026 about this. But also some of this is quite old, and so I think it's important to see this in context. Sometimes we see these AI developments and just think, "Wow, how did they come up with that out of out of nothing?" And in reality, all these models are just slow incremental developments generally of previous models here. So we'll try to tie some of that together today. So first thing we want to look at is encoder decoder models, and these are actually coming more from language there, the idea. And again, next class, I think the 6117, you'll look more, and even later in this class when we get to transformers, we'll talk about encodings. But the idea is that you'll take some words and you'll encode them into a set of a vector of numbers. And this is some internal representation of this sentence here. And then we'll feed that to a decoder and we'll decode that back into words. So we create this internal representation here. So again, we have some world states, some, again, words or images and stuff. We encode that into some what we often call a latent space or meaning space. I think today the term latent space is more often used for this. And then from that, we can decode that. So again, we kind of like based on your brain, you haven't, when you hear a set of words or read some words, you build an internal representation, a meaning space of those words. And then from that, you can generate language or images or whatever. This comes again from, a lot of it comes from Google Translation stuff, where they would take a sentence in, encode it into a meaning space, and then they'd have trained different decoders that would generate text in different languages, so that would allow them to easily translate from almost any language to another number of other languages here. So now, kind of based on this in the image world now, remember, we just looked at convolutional neural networks where they had these layers of convolutions here. And so we're going to look at something similar to that. But rather than having a set of convolution going down to some internal representation and then training a classification model off of that, we're going to have some an image start off here and very large, like 500 by 500 pixels or even bigger there. And we're going to convert that, use that convolutional layers to detect some features out of that. And then we're going to use we're going to shrink that down and to a smaller size image here, and then detect some more features, shrink that down, and detect some more features, and so on. And eventually, we're going to have our meaning or our latent space here. And then again, we can train a traditional neural network to look at this feature space here and do something with it. And the idea then is that once we have that, we're going to then generate the image by building up a small image, a larger image, an even larger image, and then often the original size image here. So that was the original model. A lot of people tried that, and it had some issues. And so UNet, what the developers of UNet here added this sort of stuff, so that when you're trying to build a 200 by 200 pixel image, you're not only seeing the meaning space from that, you're also seeing the original image. So this sort of model is used like a lot in like cancer detection or image detection, where we want to highlight like the cancer cells in an image, or the salt or oil deposits in a scan of the earth or anything like that. So the idea is that at this point we're trying to detect, or at this point we're given the original image or the feature space from a smaller size image, and we're looking at that and this encoded meaning space here to figure things out. So this is the UNet model, and you'll still see this again. It's not used that much by itself these days, but it is a component in a lot of the more advanced models here. So again, this is a little article where this comes from. You can look at that if you want here. So let's talk about image generation. Um, Originally, we used something called generative adversary networks, GANs. These are not used anymore, and but I just mention them because a lot of people might mention, compare this to GANs, or in the past we used to use GANs there. And this was an interesting network. We would start with some random noise, and we would have it generate a fake image here, and then we'd also have a training set of real images. And then we'd have a separate neural network called a discriminator, and it was trained to look at both a real image and a counterfeit, a fake image, and tell the difference between these two here, and generate just say real or fake. And slowly, initially, the images generated were very bad, were very noisy, and it was easy for the discriminator to detect those. But as the discriminator got better, it fed information back to this generator. This is all trained, this whole double network was trained at once with back propagation. And so the generator got better, and the discriminator got better. But it was really hard to train, but when it did, it worked quite well. But again, it was very difficult to get the right set of images and often got a little sidetracked here. But it's interesting, it started with random noise, and that's one thing we'll see. This idea of random noise using to generate images comes from this, which we no longer use. So diffusion models are used a lot for image generation. They're actually now being used for, this model is applied for like text generation, sentence generation, lots of other things. So this idea has grown, but it started with image generation, and that's where we'll look at it here. And it is still being used for image generation. There's some good resources. Google, you might have to log into your CSS account to view this. Hugging Face, I don't know if we mentioned Hugging Face before. They're a well-known French company with lots of data, lots of open source models and stuff. So like anyone doing research like this summer, I'm working with a student, we're training a robot arm to grab things. We're using a lot of stuff off of Hugging Face, and we're using Hugging Face to store our training data there also. But they have a guide to one of the common diffusion models that's open source is called Stable Diffusion there. So they have a guide to that. I think some of this is nice to see in video tutorials. So I'm a big fan of Three Blues, One Browns, and they actually have a video that was actually created by Welsh Lab on how this works there. IBM has some really good videos on tutorials on AI. If you haven't watched any of the IBM tutorials, you should start looking at those. And so this is their diffusion model there. And this is another one here for this. So let's just point out a couple things here. Let me load this. Okay, so again, he'll walk you through this, but again, they're talking about these diffusion models and how they start with an image and slowly add noise to it until they get fuzzy, a very, a random noise, basically, image through like 1,000 steps. And then they go backwards and they're going to train they're going to train a network that'll take this image and remove some noise from it. And so that process of training a network to take an image with some noise and remove some noise to it will eventually do where we're training a model to start with random noise and generate an image from it. So again, and he's talking about they're trading. What's in his is a convolutional neural network called UNet. So the model they use to do this is UNet underneath, as part of this larger system, larger model for this. And so again, that's why I wanted to mention this UNet and how it fits in. So, this is it's an old model, but we're still seeing it here. Um, AI assembly, this is one of these nice videos I like because they explain this on 4 different levels. So again, sometimes the math and stuff gets a little hard initially on some of these models. Well, again, depending on how much math you like, when you step into these models, let me see if I can get, yeah. um, again, some of the math of these diffusion models, these are based on some physics concepts, and people get really excited in math. And the math is really cool underneath. But again, if you're not a big fan of it, something like this, where we're displaying it, we're just talking about it at level 2, is nice because they do a good job of explaining this, how we, again, start with the clean image, generate, add more noise to it till we get to a noisy image, and then reverse that process and train a network to go from each of these steps back. But then again, we get into this whole math of this also if you want to dive deeper, if you want to watch more of that. So, okay. So that's I watched some of these videos to get an understanding of these diffusion models. Now, how do we get these models where we can type in, like I want a picture of, and type in a text prompt there. So again, this is a article by Geeks for Geeks on creating images with text prompts. And again, this shows this idea here is that we start with some image, we encode it. Here's our encoder and our decoder. So again, that comes from long ago. So this is our encoder. And here we're working in our latent space. We have an internal representation of that image, a vector basically of numbers. We do forward diffusion to, again, add noise to it. And then we do UNet to remove that noise, a denoise part of that here, and generate this image. And then we have our decoder to generate the actual image here. Now, with UNet, if you remember, UNet's really neat because again, we feed these images here. It's already set to get inputs from 2 different things at each layer. You're getting the image from the original, an input from the original image, and the input from the kind of lower down layer here. And what we do is we add another input in here there, and that's what they're showing here. Is in some of these critical areas, we're adding inputs, and they can be different things. But in this case, let's just say it's a text prompt. So we're encoding text into a vector. And again, when we get into actually your next course, but also a little bit in transformers, we'll see how we convert text into an encoded set of vector numbers here. But that is then fed into UNet along with these original fuzzy images, and UNet is trained to denoise this. What's nice about this training system, as you can see, is that we have an image. We're going to recreate that image, and the text prompt is what should describe that image here. So all we need for this training is a bunch of images with descriptions tied to them, text prompts, and then we can feed the image, encode it, do this, feed the text prompt, encode that, feed that in here, and get it back and try to recreate the original image. So we basically are taking our image, encoding it into this latent space, this internal representation, this condensed version of it, and then from that generating the image back again. It's kind of like if you told someone, if you looked at a picture and described the picture to an artist and have that artist then try to recreate that image just from your description. It's kind of like that. We create an internal representation, a minimal, representation that still would allow us to recreate the original image. So if you haven't tried any of these image generation stuff, here are some links. There are more out here. These are just a couple I have to link in, but you should, if you haven't tried them, you certainly should here. And then for a class, we'll be talking about some of these ethical issues here related to this. there are lots of ethical issues related to this, so we're just touching on some of these here. There are whole classes devoted to the ethics and legality and stuff like that of AI and image generation. So, but I think it is important to at least start thinking about some of the issues that are being raised here. So this is just us at least thinking about what are some of the issues that are tied to this. Okay, that's enough for this. Hope you enjoyed this video.